Good morning. Today we are going to discuss a module 1 BJT AC analysis, a transistor modeling, that specifically RE model. The objective of today's class is to discuss a frequency response of an amplifier, why that modeling is needed, then a different types of modeling of a transistor, and then in detail we are going to discuss a common base and common emitter RE model. The frequency response of an amplifier as shown in that figure 1. That amplifier circuit as shown in that figure, which is a voltage divider common emitter amplifier, a corresponding frequency response as shown in that figure. When that if you observe the frequency response of an amplifier, that gain of the amplifier varies as the frequency varies at low frequencies, as the gain of the amplifier decreases as the gain of the amplifier decreases as the frequency increases. The gain of the amplifier increases, that is due to the coupling capacitor Cc or C1 and resistance Ri. If you measure that voltage at this point, the voltage at this point is on Vi dash, where if the input voltage varies due to the reactive component, as the frequency increases, the gain of the input Vi dash is also varies. Means as the frequency increases, the reactance of a capacitor decreases and then Vi dash increases. As the Vi dash increases, the gain is also increases. As the frequency increases, the capacitance of the reactance of a capacitor almost constant and it is acting as a short circuit, and then output voltage V0 remains constant as the input voltage constant. At the high frequency, the gain of the amplifier decreases, that is due to the coupling capacitors, that is nothing but a Ce of the emitter and a Cc at the common base collector junction. Because of these stray capacitance of a transistor, the gain of the amplifier decreases at high frequency. Therefore, it is necessary to model a transistor at low frequency and high frequency separately. The need for a transistor modeling, why we have to need? The transistor small signal amplifier can be considered a linear for most applications. A best model approximation of the actual behavior of a semiconductor device under specific operating conditions, including circuit elements. In the previous class, we were discussing that a diode is modeled as RF when the diode is forward biased and R when the diode is reverse biased. Means this transistor can be replaced by using these two components. Therefore, you have to approximate this transistor as a linear model and then using a piecewise linear diode model, and then we can replace the diode two junctions with RF and RR respectively. The transistor models transistor can be modeled as two types. One is an RE model and other one is an hybrid model. Means in case of an RE model, any region of operation, means either that operating point of a transistor, consider output characteristics, that operating point is either closer to the saturation region or operating point is closer to the cutoff region. In each and every condition, it can be used. But disadvantage of this RE model is output impedance is not possible to determine and accuracy of this analysis is very poor. The other model is an hybrid model. This is limited to the particular operating conditions, but it gives a more accuracy. This hybrid model, H parameter can be designed or modeled by using that a transistor parameters. Means here we have to distinguish this RE model and a hybrid model. That RE model is to be designed modeled based on the diode parameters, and hybrid model is to be based on that transistor parameters. Now let us consider first an RE model of a transistor, that is common base configuration. If you consider a transistor RE model, that is a common base configuration as shown in that a transistor RE model as shown in that figure. If you consider a common base configuration, that input is applied between the emitter and a base, and output is to be taken across the collector and a base junction, where that input current is IE, output current is IC, and then current flowing to that base is denoted with IB. When this transistor is in active region, that emitter base junction is always forward biased and collector base junction is always reverse biased. When the emitter base junction is forward biased, then this junction can be replaced with a diode D as shown in figure 2b. When the diode is reverse biased, means the collector base junction is reverse biased, then that current flowing through a reverse biased junction is a constant until that breakdown. Because of that reason, that a common collector means collector base junction is replaced with a constant current source. But already we derived that its impedance is to be output resistance of an infinity, it is an infinity. Therefore, that a collector base emitter junction resistance is infinity, and then it is replaced with a constant current source of that is equal to alpha times IE. That RE model of this common base in the figure 2b were shown that a common emitter base junction is replaced with a diode and a collector base junction is replaced with a constant current source alpha times I. Then this diode can, when the diode is forward biased, then this low signal model of this diode is nothing but RF. Similarly, identical to the a diode resistance, then this diode is to be replaced with an RE. A suffix E is indicating that R resistance, R is resistance, that suffix E is indicating the resistance of a emitter base junction, where base is grounded, then that resistance is to be denoted with an RE. Where when you are defining this RE model, then you have to define that analyzing this transistor, means when you are defining a transistor parameters or the analyzing this transistor amplifier, we need to replace this transistor with the diagram as shown in that figure 2c, where you are analyzing the transistor amplifier in a common base configuration. It is necessary to determine what are the parameters you are going to evaluate. That is the question arises. When you want to measure a parameters, that major parameters of this is nothing but a input resistance ZB, output resistance Z0, a voltage gain AV, current gain AI. Then how do you determine this? That means when you want to determine input impedance, means you are looking into the transistor from emitter base junction. When this impedance is known as ZB, when you are looking into the impedance at this point, if you are applying KVL, we know that already input is Vi, output is to be taken across a collector base junction region V0. When you want to measure this point, because only one component is there, it is a constant current source, then whatever the input impedance, that is ZB, is nothing but RE. You want to measure the output impedance Z0 when you are looking into a collector base junction. When looking into the collector base junction, that means you have to measure the output impedance Z0, you have to set Vi is equal to 0. When Vi is equal to 0, emitter current is also 0, then this constant current source is acting as a open circuit, hence that output impedance Z0 is equal to infinity. we are already specified when we are discussing that need for an RE model, therefore Z0 does not give any account, hence this RE model, the drawback of this RE model. Next we have to define the current gain. A current gain is to be, you have to define that output current, you have to define that output current I0 by an input current II, that output current is IC, input current is IE, then IC equal to alpha times IE, then that current gain AI is equal to alpha. To determine the voltage gain of a transistor, when this circuit common collector base junction is open circuited, hence then the output voltage V0, whatever the input voltage you are going to apply. To determine that output current means voltage gain of this transistor, you have to connect a load resistance RL here, and then current flowing is up from that base to collector. Then that output is to be taken across the collector base junction, where V0 equal to I0 minus I0 into RL, where I0 is nothing but this collector current and output currents are opposite to that direction, then that minus I0 is equal to IC times RL, where IC is nothing but alpha times IE RL, where IE is given by that input current is equal to applied voltage Vi divided by that input impedance ZB. Hence, that output voltage gain V0 by Vi AB equal to alpha times RL by ZB, where ZB is nothing but alpha times RL by small resistance RE. These are the parameters you are going to measure or determine for any configurations. In general, for a common base configuration, we determine these parameters. For any other configurations also, we are going to calculate the input impedance with biasing and output impedance Z0 and a voltage gain AB and a current gain AI. These are the 4 parameters you need to calculate. To determining these 4 parameters, first thing is you have to know the wiring circuits or a connection diagram, and then this transistor is replaced with its equivalent diagram as shown in that figure 2C, and then later you have to analyze, and then you have to calculate a input output impedances, voltage gain and current gain. The figure 2D shown for the NP equivalent circuit of an RE model of a transistor for a NPN transistor, where NPN transistor means that current direction, diode direction, because here in case of a PNP transistor current is outward, but in case of an NPN transistor current is inward. Sorry, this is for the PNP transistor, NPN transistor is outward, therefore the direction of a diode is reversed in case of the figure 2D when compared to that figure 2B. That analysis of this NPN transistor and PNP transistors provides the same results. With this a basic introduction of that common base configuration, this gives a platform for analysis of a CE configuration. Whatever we discussed earlier, from until that common base configuration from a diodes, a transistor parameters, a frequency response of an amplifier, as well as the common base configuration, these are helps to analyze the RE model or a common emitter configuration. Now let us consider a common emitter configuration. In a RE model common emitter configuration, that figure 3A has shown a NPN, a common emitter configuration. This base emitter collector as shown in that figure. Means first, when you have to modeling a transistor, identifying the terminals of a transistor. Once identifying the terminals of a transistor, then already we know that a input circuit means a base emitter junction is forward biased and collector base junction is reverse biased, but output is to be taken across the emitter and a collector and a emitter. Here when this a base is common for the input and the output, that figure shown in 3B. in that 3B, the diode means that base collector, base emitter junction is replaced with a diode D, because emitter base junction is forward biased and collector base junction is reverse biased, then that is replaced with a constant current source, that IC, where input current is IB and output current is IC. Already we know that from this transistor current gains that a current IC and IB related with a beta. Therefore, you can say that IC is equal to beta times IB. This equivalent model is used to analyze when this diode D is replaced with RE from the previous discussion, and voltage drop across this point base emitter junction is on VBE, and then current flowing through that. The current flowing through this emitter resistance is IE. When you want to determine that analysis, this is not a complete equivalent model. I want to analyze the complete equivalent model. First, we have to analyzing this. What is the input? Once again, that 4 parameters you are going to measure: a input resistance, output impedance, a voltage gain AV, current gain AI. For this case, we need to determine input impedance. When you are determining an input impedance, that is to be ZB is defined as a voltage VBE divided by IB. That is the definition of the input impedance. We need to define that a ZB, you are applying KVL to the path shown in that figure. That voltage is across this point, applied voltage on VBE, there is no resistance, then minus IE times RE equal to 0. By definition, you have to solve for this. VBE is equal to IE times RE. When VBE is equal to IE times RE, then actually by definition a ZB input impedance is given by VBE by IB or VI by IB. Then you have to substitute, we know that already, that is IE equal to IB plus IC, where IC is nothing but a beta times IB, therefore IB plus beta times IB. That IE is equal to IB into 1 plus beta. But beta is of a transistor is a ratio of the collector current to the base current. Its value is very high, hence beta, if that beta is much greater than 1, then IE is approximately equal to IB. If that IE is equal to, if the IE is approximately equal to IB, then substituting in this equation 1, we will get that ZB is equal to VBE by IB, this is equal to beta times RE. This is one of the important equations we need to remember to solve the numericals. And similarly, when you are looking into the output impedance Z0, when you have to set the output impedance Z0, you have to output impedance means you are looking into the collector emitter junction. When you are looking into the collector emitter junction, first step is you have to set Vi is equal to 0. When Vi is equal to 0, it is acting as a short circuit. And then due to the input voltage, that collector current IC, that beta times a constant current source, is acting as a open circuited. When the collector, this junction is open circuited, and then that parallel combination of this output impedance, that Z0 is equal to infinity. Means if that IB is 0, but Z0 is equal to infinity, but due to the, because already we defined a transistor is a transfer resistance, this is the transistor, a emitter, base, a collector. Already we know that this junction is forward biased, and then this resistance is denoted with RF, that is shown in that point VE, and then this junction is reverse biased, it is acting as an open circuit. Still, because of that charge carriers are crossing over this junction, there is a conductivity between the emitter and a collector. Hence, in the case of a common emitter configuration, that we can replace this, means constant current source is in parallel with the resistance R naught. This R naught is lies in between that a RF and RR. Means this RF is the forward resistance of this junction, emitter base junction, RR is the collector base junction, it is on infinity. Then this R naught is to be a conductivity of that emitter collector, it is lies in between this RF, small means that is from low resistance and the high resistance infinity. Hence here in this circuit diagram we are not shown that R naught, but still that output impedance is equal to infinity. Apart from this, means when this is an RE model, we are defining that input impedance and an output impedance, then this figure 3b and 3c are replaced with figure and replaced with a transistor equivalent model as shown in figure 3d. Means here means that a figure 3c is replaced, means that beta times RE, that question marks why you have to replace, because in a common base configuration you are simply says RE, but here that resistance is to be replaced with beta times RE. Can you guess why it is? Means because if you consider the transistor model, a figure 3b, means in the figure 3b we defined this is a base and then this is resistance RE, current flowing through this is IE, and then current a constant current source, this is beta times IC as shown in that figure 3c. You are using here, why you have to, instead of RE, why you have to replace that beta times RE? That is the question. Can you guess it? How do you define? Means we know that by definition that input current flowing through that base is IB, but here that current RE is to be the resistance of a emitter, that current flowing through this is an IE. We know that IE equal to a IC plus IB, this is nothing but IC is nothing but a beta times IB plus IB, this is equal to IB plus into 1 plus beta. Already defined when you are discussing a input impedance where beta is much greater than 1, then this IE is approximately equal to beta times IB. Then we have to replace this IE is equal to that current flowing through this is nothing but beta times IB. Then what is the voltage up across this complete thing? That emitter resistance, this is nothing but beta IB times RE. This can be defined as that beta times RE, IB times RE can be rewritten as this IB into beta times RE. This implies that when this IB, current flowing through this IB, already we are defined, that is in this point IB, and then that current flowing through this RE is IE. You have to defining that, you have to embedded this beta into the resistance, then this RE of a common base configuration is replaced with beta times RE. Then that current is to be constant current source is to be denoted with beta times IB, and then we are shown one more resistance R naught. This is due to the, already we discussed, that is due to the conductivity between the collector and the emitter. Then this is given by denoted by an R naught, where R naught value lies in between 0 and infinity or RF and infinity. For this, if a transistor is to be replaced with this equivalent model in compared to that figure 3C, figure 3C is complex, then in a case of a common emitter configuration, the transistor base collector emitter, this can be replaced with that shown in figure 3D of an RE model. If you are using this RE model, it is easy to determine the common emitter parameters. In a common emitter parameters means you are going to define this an input ZB, and when you are looking into this, a junction collector emitter junction is denoted with Z0, and also we are going to determine an AV and a current gain AI. For this circuit, easily we can determine. For this circuit, we are going to determine that a input impedance means you are applying KVL to this, then ZB is equal to VI by IB. When you are looking into this diagram, then you are going to get beta times RE. This is the one important equation. Next, we have to determine the collector emitter junction, that R0. When you want to determine a collector emitter junction R0, you are applying that when looking back into the collector emitter junction. When a collector emitter junction means you have to determine Z0, we need to set that Vi is equal to 0. When Vi is equal to 0 means there where the input is applied between this terminal. When Vi is equal to 0, then current IB is also 0. When current IB 0, then this a constant current source is acting as a open circuit, hence that output impedance Z0 is equal to R0. This is another important equation. Next, we have to determine the current gain and the voltage gain. This resistance value is lies in between 0 and infinity. It is about a 50 kilo ohms to 80 kilo ohms. Next, we need to determine on voltage gain. Voltage gain AV is equal to V0 by Vi. When voltage gain AV is equal to V0 by Vi, then we need to calculate an open circuit. Because this is an open circuit, then you have to connect an external resistance RL. This RL current flowing through this is in this direction. When that current flowing in this direction, then AV is equal to, our current is to be flowing this direction, then a V0 is equal to, that current is I0 into RL, then I0 is equal to minus IC, then V0 is equal to minus IC times RL, where IC is equal to, approximately equal to a beta times IB RL, where IB from this earlier equation we know that IB is equal to a ZB into where a IB is given by ZB ZB is given by ZB is equal to a Vi by IB. If you substituting this equation, a V0 equal to minus beta that Vi by ZB into RL, then the voltage gain V0 equal to that beta times minus beta times RL by beta times RE, then that voltage gain of a common emitter configuration is given by simply minus RL by RE, where that negative sign is indicating that a phase difference between the input and a output signal. Means when the input signal is applied, then this is an input signal, then the signal is amplified, and then that output signal is out of phase with respect to the an input signal. Means that phase difference between the input and output is given by this ratio V0 by Vi is nothing but on AV. This is given by this another important equation, that is AV is equal to minus RL by RE. Next, we need to calculate a current gain. Current gain is given by this current IL. That current is to be flowing in this direction. Then that this current flowing through this is given by I naught. The current flowing through that input circuit is IB. That current gain AI is equal to I naught by IB, where I naught is equal to minus IC. Then AI is equal to a minus IC by IB. Then what is IC? If you are assuming that R naught is large, then in the earlier case that IC is approximately equal to beta times IB. But this IC is nothing but I naught is the current flowing through the load resistance RL. Where current is to be flowing through the load resistance RL, then this circuit, that RL and R naught combination, is driven by a constant current source. Because of that reason, means already we know that a transistor in a two parallel network, means currents flowing through in a parallel network, is given by IC is the current flowing through this circuit. IC is equal to that a total current, that is nothing but beta times IB, and opposite branch resistance R naught divided by and total resistance, that is R naught plus RL. Hence, that current gain AI equal to beta, current gain A is equal to, current gain A is given by minus IC by IB. From the figure, it is, we know that this is nothing but a beta times IB R naught divided by R naught plus RL divided by IB. Hence, this current gain A is equal to beta times R naught divided by R naught plus RL. This is an actual expression or the exact analysis of a current gain of a common emitter configuration. For a common emitter configuration, this current gain is given by this beta R naught divided by R naught plus RL. If R naught is much greater than RL, normally I already specified that R naught is about 80 kilo ohms about, and then RL is to be as low as possible, then this, under this condition, AI is approximately equal to a transistor current gain, that is IC by IB, that is equal to beta only. For this common emitter configuration, this we are studied that basically that beta is studied, that is for a common emitter configuration, that ZB equal to beta times RE, and output impedance Z0 is equal to R naught. Under ideal condition, Z0 is equal to infinity. For the ideal case, a voltage gain AV is equal to minus RL by RE, and a current gain AI is equal to approximately equal to beta. It is an approximate solution. That exact solution is given by beta times R naught divided by R naught plus RL. Means whenever you have to connect a load resistance RL, that current gain is slightly decreases. Next, let us consider using this a common emitter configuration. You have to use applied for a biasing circuits. This is a complete analysis of the circuit analysis. You have to consider a fixed bias, a CE configuration. In a fixed bias circuit, you have to write this is your transistor, base, this is emitter, a collector, it is connecting to the RC, and then this resistance RB is a biasing resistance, and then you are connecting to the source. You are applying that input across the base VI. For this circuit analysis, using a common emitter configuration, first thing is identify the a terminals of a transistor. This transistor is replaced with its equivalent model, that is beta times Re, as shown in that figure 3D, beta times Re, and then a constant current source, that is beta times Ib, and then there is a resistance R0. This is your collector, emitter, and base. Means you are just to transfer this transistor with its equivalent model, that is nothing but a beta Re. Later things is you have to transfer in the that need for the modeling, you have to transfer this circuit elements. To transfer these circuit elements, then you have to set that VCC is connecting to the ground. When the VCC is connecting to the ground, then that collector current, this current flowing through, this is your IC, this is IB, and then this is IE. When the current collector, that VCC is grounded, then this collector resistance RC is lies in between the collector and a ground. But emitter is already grounded. This is nothing but a collector is connecting between the collector and a emitter. And similarly, when this is grounded, this RB is lies in between the base and a collector. Here we are apply VI. Already at low frequency or mid frequency range, this coupling capacitor Cc is acting as a short circuit. There is no more exist. Then you are analyzing this circuit. This circuit, this whatever the things shown in that a block diagram is nothing but a equivalent circuit of a RE model of a transistor, and then you have to transfer the external components RC and RB by setting that VCC is equal to 0. When VCC is equal to 0, then it is a grounded, means this is nothing but directly it is connecting to the emitter, and then it is transferred RC and RB at the output and input circuit respectively. For this analysis of this circuit diagram, you have to connect, you have to measure with respect to this point is already we defined ZB, and then you are looking into this of a transistor is nothing but Zi, and then you are looking into this already we defined earlierly, that is Z0, and then if you consider the output resistance RC, then this is denoted with Z0 dash. That current flowing through this is IB, and this current is IC, and then the other current because from this that collector current is flowing in this diagram, that is a emitter to ground, hence this is to be output current is to be flowing in this direction. This is equal to, you have to set output is to be taken across V0. For this circuit analysis, you have to once again applying a KCL and KVL. Here that KCL and KVL is not necessary, because that thing is, because when you are determining on ZB, that only that out input circuit resistance is the only resistance RB is there. You can determining by just observing when you are looking into the a base emitter junction, this resistance existing between this base and emitter resistance is nothing but a beta times Re. We can define for a common base configuration ZB is equal to a beta times Re. That is one expression, that is one of the important expression, and you have to determine that Zi, means when that circuit is biased with a fixed bias or a voltage divider or any biasing circuit, you have to consider that to determine the input impedance by considering the resistance RB, then this Zi is nothing but a parallel, means this entire transistor is replaced with a input resistance ZB, means we can write there is a RB, and then this entire circuit, when you are looking into the base emitter junction, then that entire circuit is to be replaced with its equivalent resistance, that is nothing but ZB. When looking into this direction, or means into the base emitter junction, these two are in parallel, then that Zi is nothing but RB is in parallel with ZB. This is nothing but RB is in parallel with beta times Re. If this is the exact analysis of the input impedance when that a biasing resistance is considered. If that RB is much greater than beta times Re, what is the effect on that input impedance? Can you think about it? Means when this Zi is beta times Re in a parallel combination, that equivalent resistance of any two resistance is always less than smaller resistance value. Because of this smaller resistance value, then Zi is approximately equal to beta times Re, means that is very close to that. Even if that biasing resistance is added, due to that biasing resistance, that effect on the input impedance of a transistor is slightly varies or slightly less than that beta times Re. Next, let us consider the output impedance Z0. To determine the output impedance, of a transistor circuit, biasing circuit, this is given by V0 by. When you are looking into this, first thing is you have to set Vi is equal to 0. Means according to the Thevenin's equivalent circuit, either set Vi is equal to 0. If the current source, you have to replace with Ii is equal to 0. When Vi is equal to 0 means it is acting as a short circuit. When this Vi is 0, then Ib is 0. Then this current beta times Ib becomes 0, means it is a open circuit. Then you are looking into this side, collector base junction Z0 is equal to R0. In the other input impedance Z0 dash, means this, from you are looking from this side, this entire circuit is to be replaced with its equivalent resistance value, that is nothing but a Z0. When you are looking into the Z0, then this is Z0 is Z0 means for this circuit we can say that this is your Z0 is in parallel with RC. We are looking into the terminals of a collector emitter junction. When you are looking into this, the Z0 dash is nothing but a parallel combination of Z0 is in parallel with RC, it is nothing but R0 is in parallel with RC, where that Z0 dash equal to approximately equal to RC, because that R0 is much greater than RC. If you are conducting an experiment in your laboratory, either using any fixed bias circuit or a voltage divider biasing circuit, your input impedance is approximately equal to beta times Re, and beta is already defined. A resistance Re is to be obtained by calculating by is equal to, because it is a diode resistance, it is given by 26 millivolts divided by IE. Re is given by 26 millivolts by IE, because we know that a current flowing through the emitter, and we can able to determine Re from this circuit, and then beta is already given from the data sheets, and then we can easily identify, and then you have to compare your results with what you measured. And similarly, for the output impedance of a transistor configuration, that Z0 dash is approximately equal to RC. Other two parameters of a transistors are a current gain and voltage gain. Current gain AI is equal to I0 by II, where II is the current flowing through this. Where current gain, because earlier we defined that is nothing but IB by IC, current gain when there is no biasing. When the biasing is introduced, because of this biasing, that current flowing through that IB is slightly reduced. Then that is given by current gain of a transistor is given by AI by IA is equal to I0 by II. What is I0? I0 is nothing but this current and this current IC are in the flowing the same direction. Therefore, I0 is equal to IC. Then what is IC? Already we defined. That means this is to be this entire circuit is driven by this beta times IB. Then this is equal to, means IC is equal to, because this is in the direction opposite direction, then you are going to get minus beta times IB, the total current, and opposite branch resistance R0 divided by R0 plus RC. You are going to get AI is equal to beta times IB R0 divided by R0 plus RC into II. Means here got this value beta times R0 by R0 plus RC. Then we need to find what is the relationship between IB and II. We are going to get this beta times R0 divided by R0 plus RC divided by IB by II. This IB by II is obtained by considering this circuit. IB is the current flowing through that, a beta times REI is nothing but a ZB, and then II is the current flowing, the total current flowing through this. Whenever you have to determine a current gain or a currents, always you have to apply a Kirchhoff's current law. Please keep this in your mind when you are solving a current gain or a current of a transistor parameters. When applying KCL to this point, this is driven by IB is equal to II is the total current, and this is opposite branch resistance is RB, and then total resistance is RB plus beta times RE. Then that current gain AI equal to beta times R0 divided by R0 plus RC into RB divided by RB plus beta times RE. This is the exact analysis of a current gain of a transistor. If you want to measure the approximate, this means if that beta times RE, RB is much greater than beta times RE, and R0 is RB is much greater than beta times RE, and R0 is much greater than RC, then this expression is means R0 plus RC is approximately equal to R0, and RB plus beta times RE is approximately equal to RB. Hence, you are going to get a current gain A is approximately equal to beta. Means in the earlier, even if you are using a biasing circuits or a without biasing, that current gain of a transistor is approximately equal to the beta. Already we defined this in the previous session. Next is to determine on voltage gain. A voltage gain of a transistor is given by, that is V0 by Vi. This is given denoted by, we know that already V0 is equal to, this is minus I0 RL divided by, and Vi is nothing but from the input circuit, this is nothing but IB into ZB, where I0 is nothing but, because this current I0 and IC are in the same direction, therefore you are going to get minus IC RL divided by IB ZB. If this resistance is very large when compared to that RC, then this approximately IC is approximately equal to minus beta times IB RL divided by IB by ZB. It is approximately equal to, this cancels, beta times RL. We know that already ZB, that is nothing but a beta times RE. When this is cancels, then AB is equal to minus RL by RE. These are the four important parameters are going to measure by using a common emitter configuration. Today's class, we conclude this session with a analysis of a transistor amplifier with, and also we discuss a need for an biasing and modeling, and then we analyzed that a RE model with a fixed bias circuit, and then finally we conclude that for any circuits you have to transfer a transistor with its equivalent model, and then transfer that external components RB and RC while setting that VCC is the ground, and then you have to analyze that circuit for the four important parameters AB, AI, ZB and Z0, Z0 dash and Zi. These are the four important. Means to analyzing this common emitter configuration of a RE model, no need to remember that equations, you need to remember this circuit diagram, and then you need to remember that equivalent circuit of a transistor. Later you have to transfer into the equivalent model and then analyze, you are going to get these values easily. Thank you.